A long time ago, all we could do was look up at the stars and wonder what they were. Then we learned, with the help of telescopes and technology, to extend our human senses farther. Farther than those first humans could ever imagine. But we haven't reached the end yet. We know there are more wonders out there. We know there is farther yet to see. If we are seeking new views of our universe and discoveries that we can barely imagine today, we need a completely new way to see. Humanity needs to open fresh eyes to see our universe in a way we never have before. Welcome to NASA's Goddard Space Flight Center. I'm Michelle Thaller. In just a few weeks, NASA and its European partner ESA will launch the James Webb Space Telescope, a colossal leap forward in humanity's quest to understand our place in the universe and our part in a story that stretches back to the beginning of time. Today I have the great privilege of hosting a conversation about the inner workings of the Webb telescope, the largest and most ambitious observatory ever launched into space. While the science goals of Webb promise the beginning of a new understanding of our universe, the technology of Webb is a marvel in itself. And so to get this conversation started, I'm joined by Eric Smith, the program scientist for the Webb telescope. Good to be here with you, Eric. I'll put my mask on. Yeah. That's right.
Hi, Michelle.
Hi.
It's great to be here.
Absolutely. Tell us a bit about the history of Webb and how it fits in.
Sure. Well, actually, to continue the story about how telescopes and the technology change our view of the universe, I actually want to start in the 1840s with a telescope that was known by the fantastic name of the Leviathan of Parsonstown. This 6-foot diameter telescope was used to study nebulae, which were clouds in the sky that they didn't really understand what they were comprised of. And what you see on the screen here is a drawing of what we now know is a galaxy. This was made by William Parsons back, I think, in 1845. Now, if we fast forward about 70 years, the world has a new largest telescope. It's the 100-inch on Mount Wilson, and that was used by Edwin Hubble, Hubble the man in this case, and he used this telescope to study these galaxies. By then, we know they're galaxies, and what he found was that the farther away the galaxy was from us, the faster it's moving. He discovers the expansion of the universe with this new telescope that he has. And you can actually trace the arc of a lot of technology and science and astronomy for the 20th century of more or less a chase of galaxies for seeking an ever farther galaxy, trying to find the very first galaxies. Well, if we move to the end of the 20th century, we deploy the most powerful telescope we've ever had, the Hubble Space Telescope. It too attempts to find these first galaxies. And you'll also see, as the pictures go by here, a comparison of what the Earl of Ross drew in 1840 to the Hubble's view of M51 galaxy. So Hubble itself tries to find these first galaxies, and it can't. So we know we need to have yet another kind of telescope with even more amazing instruments. That's the James Webb Space Telescope. So not only will it help us complete this chase of galaxies, but it promises to allow us to explore the atmospheres of exoplanets, alien worlds, study how stars form in our own galaxy. And today you'll hear about this amazing telescope and the instruments that will make that all possible.
That's absolutely wonderful. Thank you so much for joining us, Eric.
My pleasure.
So as we talk about the instruments, one of the first things we need to do is talk about this amazing giant mirror. And there's nobody better to speak to us about that than Lee Feinberg. He is the optical telescope manager for Webb here at Goddard Space Flight Center. So Lee, talk to us about the incredible mirror that all these instruments will use.
Well, at 6.5 meters, the primary mirror was too big to fit in a rocket. So we designed it so that it would unfold in space, and it does it like a drop leaf table. But in order to do that, we needed mirrors that could be in segments. And so we've designed the segments to be hexagonal shaped. And that's really nice because all 18 mirrors have the same mechanical design. So we get a lot of economies of scale in how we made the mirrors. And they're actually made out of beryllium. And beryllium is really ideal for these very cold temperatures. So that's why we chose beryllium. And we coat them with gold, a very thin layer of gold. But gold is ideal for the infrared wavelengths, very high reflection. And that lets us see as far as we can and capture all the photons.
It's absolutely wonderful. Is there anything else you'd like to add about the mirror before we go?
No, I mean, the mirror on Webb is actually much larger than previous space telescopes. In fact, it's lighter as well. The primary mirror for the Hubble Space Telescope is 10 times heavier per unit area. So we had to make a much lighter mirror. And this mirror is also, if you compare it against like an infrared telescope, like the Spitzer Space Telescope, which NASA launched many years ago, the Webb telescope is actually 50 times larger. So it has a lot more ability to collect photons, and that makes it much more sensitive. Yet it actually works at shorter wavelengths than the Spitzer Space Telescope, almost down to the wavelengths that Hubble works at.
Absolutely excellent. Well, thank you so much for joining us, and we'll see you for the questions later on.
Okay.
All right. So the next person who will be joining us is Marcia Ricci. And Marcia Ricci is the principal investigator for the NIRCam instrument. So she's actually speaking us today from the University of Arizona. So Marcia, are you joining us?
I'm here and very happy to talk about NIRCam.
Please go ahead.
Okay, well, NIRCam is a dual-purpose instrument. It is both a science camera and the wavefront sensor. So as Lee mentioned, the telescope mirror comes in 18 segments and they have to be aligned. And so you can see NIRCam is also dual in the sense of how it was constructed. It has two identical halves bolted together, and that gives us the redundancy so that NIRCam can always be available to align those mirror segments. And this is a big advantage for deep surveys because we can look at twice the sky. And what you're also going to see is a light sensor package, aka detector package, in the test tour here on campus where we gave it its final run through. It has 16 megapixels, with the full instrument having 40 megapixels, which is a lot of pixels for sitting a mile away, a million miles away from Earth. Now, you might ask, what are we going to do with all those pixels? And we have several very big science projects that we're going to do. One of the things that was part of the original plan for the telescope is to look for the very first galaxies to form after the Big Bang. And we know, and here you can see the Big Dipper, and we're going to zoom in to the kind of image that Hubble took as best it can do on these very distant, very red objects. And shortly, a red blob will appear, and that red blob, we're seeing the light from this galaxy as it left only 400 million years after the Big Bang, about 3% the age of the universe. This particular galaxy is extremely bright, and we think it's only the tip of the iceberg of the kinds of galaxies that Webb is going to detect, and we hope we get even closer in time to the Big Bang than what this galaxy is. Now, looking for distant galaxies is not the only science that NIRCam can do. It can be used for many projects, including looking at the atmospheres of planets orbiting other stars, exoplanets. And the way we're going to do that is using the transit technique. And so what we'll do is we will observe a star, a planet will pass in front of it, and the light from the star will be dimmed for a little while. And then if we analyze how that light gets dimmed and look at what colors of light come through, we can analyze the pattern and see what kinds of molecules are in that atmosphere. Now, that's not the only way that we can observe exoplanets. We also have the capability to look at them what we call directly, that is, in the light that they reflect from their parent star. And ordinarily, you can't see these planets. Here's a hypothetical rocket ship going through this exosolar system, and when you're actually there, you can see the planet. But if you move far away, like our vantage point with Webb, that planet gets lost in the glare of the sun, and you have to blot out the starlight using a dark opaque disk that we call a coronagraph. And so that's just a quick sampler of the things that we'll do with NIRCam.
Now, of course, JWST is not just an imaging camera, but it also has a lot to do with spectra as well. So now we're going to Pierre Fruy. He's actually the NIRSpec principal investigator from the European Space Agency, and he'll tell us more about this spectroscopy technique. So Pierre, welcome to our broadcast.
Yes, thanks, Michelle. I'm very happy also to be here, to be able to talk about NIRSpec. So NIRSpec, indeed, its name means near-infrared spectrograph. So it's a spectrograph And it's part of European contribution to Webb, like the mid-infrared instrument. And NIRSPEC is going to allow to probe a wide variety of astronomical objects, from the first galaxies to planets orbiting over stars. And with NIRSPEC, it's going to be achieved by analyzing spectra and not images. And NIRSPEC is a pure spectrograph. So we are all used to images, but spectrograph work a little bit differently. They are going basically to take the light from an object, as you can see on the screen, and split it into its component, creating what we call a spectrum. And spectra contain information about what the object is made, what are its physical, its chemical properties. So it's a treasure trove of information that NIRSPEC is going to put in the hands of scientists all around the world. So all JWST instruments have spectroscopic modes. As you have already heard for NIRCam, you will hear for NIRIS, and it's also the case of MIRI. And NIRSPEC is going to offer additional choices to Webb scientists. If I take one example, if we take the little red blob that Marcia presented, these very distant galaxies, they are so far away, they are located more than 13 billion light years away, that very little of their light is going to reach us. So to observe them, we are going to have to stare for hours. And this is why NIRSPEC is really designed to observe more than 200 of them at the same time, not one. And it's a very efficient use of Webb's precious time. To do that, it's equipped with a very special novel device that you see currently on the screen. These are arrays containing close to 250,000 of very tiny little doors that you can open, close at will. And to observe with NIRSPEC, scientists will pick a patch on the sky, select the objects, open the doors in front of these objects, close the doors for the others, and they will get individual spectra for this object, close to 200 at once. Okay, and that's the first example. And you will see another example for NIRIS of observing multiple objects at the same time. But sometimes scientists actually are not interested in getting 200 spectra of 200 different objects. What they want is to get as many spectra as possible from one object. And NIRSPEC can do that, like MIRI, in fact. And it's going to use what we call a slicer. It's going to slice the image of the object in 30 slices. You're going to see on the screen this image of a galaxy, and you cut it not 30 here, but in NIRSPEC it's 30. Each of these 30 slices is going to give you 30 spectra. So 30 times 30, it means you get 900 spectra at once of a given object. And with that, you're able to map beautifully the physical, kinematical, chemical properties of an extended object, a nice object like a galaxy. So that was basically to give you an overview of what can NIRSPEC do. Of course, NIRSPEC, together with NIRCam, with MIRI, with NIRIS, is going to offer really a very nice toolbox to scientists, a spectroscopic toolbox. And to conclude on this image, which was when NIRSPEC was fully assembled, really now we are ready. Now we are in JWST, we are ready, and we are waiting eagerly for launch and to start using NIRSPEC in space.
Thank you very much, Pierre. So in keeping with our theme that this is a very international collaboration, we're now going to Canada. And so for our last guest, we're talking to René Deon, and he is at the University of Montreal. René, please tell us.
Bonjour, Michel. I'm very glad to be here. So I'm going to talk to you about the Canadian. So the Canadian Space Agency is providing two key elements built by ComDev that are now known to be Honeywell. So I'm going to talk about the fine gathering sensor, which is the gather for short. So the gather is not a scientific instrument, but known as a key component of the observatory. So the gather is basically an infrared camera that look at the sky and pick up a star, and we track its movement while we take any observations with all science instruments, because there's inevitably vibrations, and if we don't correct for them, then the images would be blurred. And so what we do, we send a signal to the fine steering mirror, a small mirror inside the observatory, that we can tip and tilt 16 times per second, and we can that way get the best possible, sharpest images. And just to give you an idea how accurate the gather is, where the gather will be capable of measuring an angular displacement of the telescope equivalent to the thickness of a human hair as seen from 1 kilometer. Or if you want, it's like being able to see someone blinking from New York City, in New York City from Washington, D.C. So it has to work that accurate to get the best possible images. So on the back side of FGS, we have the scientific module of the Canadian instrument called NIRIS, which is Near Infrared Imager and Slitless Spectrograph. So NIRIS is basically an infrared camera operating on the same wavelength range as NIRCam and NIRSPEC, but and can take images like NIRCam, but mostly will be used for spectroscopic observations that Pierre described so well, and also Marcia. So in one mode, we're going to be doing transit spectroscopy that Marcia described very well, but our mode is specialized to look at very bright stars. We can disperse light over a wide wavelength range, but at the same time, making sure that we don't saturate our detector with a very special prism that will allow us to look at planets like the TRAPPIST-1 system. So here's an animation that they illustrate the technique. We're looking after the tiny sliver of light that forms the atmosphere that is filtered by the starlight. This is very difficult to do. We can do that with Hubble. Well, we're going to be able to do it much better with Webb. So we'll look at a target like TRAPPIST-1. This is the rock star of a planetary system, a system that has 7 planets transiting its star, and 3 of them are right in the habitable zone. So those planets could have life. So the big question is, do these planets have an atmosphere? And we're sure going to be looking for those planets and be able to say whether they have water, CO, and methane in one single spectrum that NIRIS will be able to take. Now, let me move to a second mode, and we move our filter wheel and we put another prism. This time we're going to do slitless spectroscopy. So it's just like NIRSPEC, but instead we take spectra of everything in our field of view. Now, this is a picture of our filter wheel. And one of them has prisms. These are dispersing elements, allowing us to take a spectra. And one special target we want to look at are galaxy clusters. Those are, we're interested in studying the galaxy and the cluster themselves. But we know that these clusters have also hidden mass, dark matter. And that cluster act like a gigantic cosmic telescope. And we hope to be able to detect very distant galaxy that happens to be behind the cluster, and using the magnification aspect of the cluster to detect those very faint galaxies. Now, slitless spectroscopy is not as efficient as doing slit spectroscopy, but the advantage is that you get everything in the field of view. So in one shot, we'll take spectra of 3,000 galaxies, so about 30 times or 20 times what NIRSPEC can do. Less efficiently, of course, but we may find some very very distant galaxies, and then tell NIRSPEC, Miri, go here, put your slit here, and let's take a spectrum of these very high distant objects. And finally, and not least, we have another mode in NIRIS that called aperture masking interferometry, which is basically inserting a mask inside the filter wheel that will block most of the light of the telescope, which is kind of strange, right? But will take the light of only 7 segments. And that way we'll be able to detect very faint companion close to the star, well within the dark spot that Marcia was mentioning. And so we're going to be able to detect new exoplanet, young gas giant planets, or planetary system, young planetary system like the one we've just shown. We're absolutely excited to get NIRIS on the sky, and we can't wait for the launch.
Thank you very much, Rene. So it's been a long journey to get ready for the launch, but it pales in comparison to this great journey ahead. Webb needs to travel 1 million miles away from Earth before it can even begin its quest for ancient light. That rocket road trip begins at an extraordinary facility located in Kourou, French Guiana. The Guiana Space Center is a tropical facility, but it's also a gateway to the stars. Few spaceports on Earth have soundscapes that include the roar of rockets, followed by the sounds of tropical jungle, once rising spires of fire disappear above the clouds. Once Webb's Ariane 5 leaves the launch pad, flight control transfers to the Mission Operations Center in Baltimore at the Space Telescope Science Institute. It's here where mission managers will not only control the spacecraft, but also gather data from the telescope's scientific instruments. So we're going to take a quick break now, and when we come back, we're going to be taking live questions from the media. If you have questions of your own on social media, you can use #NasaWebb. So join us in a few minutes, and we'll be back to actually talk to this extraordinary panel of scientists and engineers about the inner workings of the Webb telescope.
Our universe is a wild and wonderful place. In NASA's Curious Universe podcast, NASA is your tour guide. Join astronauts, scientists, and engineers on a new adventure each episode. Investigate black holes. Spend a day on the International Space Station and meet the experts behind the revolutionary James Webb Space Telescope. Find NASA's Curious Universe in your favorite podcast app or by visiting nasa.gov/podcasts.
What's out there? Let's find out. The James Webb Space Telescope Augmented Reality app. Whoa! Check out the most extraordinary scientific instrument ever designed in your own space today, only from NASA.
Welcome back to the James Webb Space Telescope pre-launch briefing. I'm Michelle Thaller, and we're here at NASA's Goddard Space Flight Center. What we're going to do now is take live questions from the media. And on social media, if you have questions of your own, just join us at #NasaWeb. So at this time, I'm going to ask the operator, do we have the first question for our panelists?
Yes, thank you. At this time, for phone line, it is star followed by number 1. Should you have a question, please unmute your line and record your name clearly as prompted. Again, with phone line questions, it is star followed by number 1. And our first question is from Bill Harwood. Your line's open.
Hey, thank you very much. Bill Harwood, CBS News. For Eric or Lee, maybe, I'm not sure, but can you provide some detail about how you get Webb into focus? I'm interested in how you'll use NearCam, I guess, to position each mirror segment, how the position actuators work, how that one works that can change the shape of a segment slightly if necessary, and just how that process works out to bring those 18 individual images down to that one diffraction-limited image. Thanks.
Yeah, sure. So when we first start, when we get the very first light from Webb, which we'll be using the NearCam instrument, the primary mirror segments are actually highly misaligned by millimeters. And so they actually act like 18 separate telescopes. They share a secondary mirror, but it's essentially like we'll get 18 images of a star when we look at just one bright star. And so our goal will be to first align those individual telescopes and then put them on top of each other. We'll take those 18 spots, we'll put them right on top of each other, but each of the telescopes are still not what we call phased up. And by phasing, I mean we have to improve the alignments by a factor of 1,000,000 so that the entire primary mirror is aligned as though it's within about a 5,000th of a diameter of a human hair. And we have a series of algorithms. It actually takes several months to do this. We start with algorithms that are easier to do, like moving the mirrors around, but as we get towards the end of these algorithms, we actually borrow a couple of algorithms, one from the Keck telescope, which does the phasing that gets us within a wavelength of light. And then at the very end, when we get the final curvature of the mirror, we're actually using an algorithm that was perfected when we were trying to determine the prescription of the Hubble spherical aberration problem. So we've borrowed from previous telescopes, and we go through the sequence of algorithms, and about 120 days in, we should have an aligned telescope.
Wonderful. Okay, we're now going to go from questions from social media. This is a question about, I believe this was probably going to NearCam, because the question is, how clear will Webb's pictures of Mars be? And so, Marcia, was that one that you could answer about the clarity of images of planetary objects like Mars?
I can answer that in part. One of the big challenges is that Mars is actually very, very bright in the infrared. And so if we want to take an image, we have to take a series of quick snapshots of just a little portion of the disk and then stitch them together. And a complication is that Mars rotates while we're taking the picture, but some schemes have been worked out, and I think when we get to the outer solar system, planets like Uranus and Neptune will be much easier to do, but they will give us images that will rival what we've seen from the Voyager flybys, but being able to do it in the infrared, we'll be able to trace out some of the molecules in those planets' atmospheres, things like methane. So we'll be able to look at Mars, but it takes a lot of effort because of how bright and how quickly it rotates.
All right, as far as some more questions from social media, I guess this one is actually one that we could have answers both with spectra and with images. The question is there a possibility to look at Oumuamua as it continues its journey away from the sun using the James Webb Space Telescope? Oumuamua was a comet that actually we believe came from another solar system. And there are more of these objects that we're going to find with the Webb. Can anybody answer the question about information on interplanetary comets, intersolar system comets?
I think if we have an adequate orbit, we could point, but I don't know if we know its orbit well enough to be able to point to where it has traveled to now in space, because it spent such a short time in the solar system, it kind of whizzed by. And whether we know exactly where it's going accurately enough to point Webb, I'm not sure.
Thank you. Would anybody like to add anything else, or shall we go move on? Okay. So the next question I believe we have is from the media. The operator?
Thank you. Our next question is from Irene Klotz. Your line's open.
Thanks very much, Irene Klotz with Aviation Week. I had a question about imaging these earliest structures after the Big Bang. Are scientists dependent on gravitational lensing with JWST, or is that something that JWST will be able to see directly?
Eric, would you like to take that?
I can
Marsha can
answer.
jump in. Sure. Marsha, please go ahead.
Right. We hope to be able to image these very distant galaxies directly without the help of gravitational lensing. And if there are ones even only a hundredth as bright as the one that I showed in the video, we'll be able to do a lot. But the virtue of gravitational lensing is that it magnifies. And so if we think about whatever ones we can see directly with NIRCam, we could go after somewhat fainter ones using gravitational lensing. So we may learn the most by combining just straightforward imaging on a blank piece of sky with something that's been gravitationally lensed.
Eric, did you want to add anything to that?
No, I was going to say exactly what Marsha said. We'll do both things
Absolutely.
with Webb.
All right. So our next question is from the news media. Please go ahead.
Bill Harwood, your line's open.
Oh, thank you very much. I think this is for Marsha, but I realize that spectra are key to Webb's operations, but the public will inevitably compare Webb's pictures with Hubble's, which everybody's familiar with. How will the images from this infrared telescope compare to what we're used to seeing from Hubble? I realize you've been asked this a million times. I'm just asking it one more. Thanks.
Well, in terms of the level of detail that we can see, we'll be able to see as fine a detail as Hubble, even though we're working at much longer wavelength. But what's going to be dramatically different is using the infrared, we see things very differently. So if you think about the image of the pillars of creation that you get from Hubble, if you take a similar picture with NIRCam, you will see through those pillars, the dust will basically disappear and you'll see stars inside. And if you go a step longer and look with MIRI, that dust that blots out the stars in the Hubble picture will become glowing warm dust and visible as a source of bright emission in MIRI images. So the images will have as much detail, but a very different character.
Thank you. Okay, let's go to another question from social media. So this one is a spectroscopy question. This might go to Pierre. Are there specific elements that we're looking for in the atmospheres of exoplanets? Is the Webb telescope tuned to look at certain elements in a spectra?
Yes, and I think it's actually applicable to Near East, to NIRCam also. One very nice thing about having an infrared vision is that infrared is a place where you get the signature of very interesting molecules. So we are talking about water, carbon monoxide, methane. So these are really molecules we are interested to learn if they are present in these planets which are orbiting over stars. So yes, definitely there's a long list actually of molecules that we will be looking for and trying to understand what is the composition of these atmospheres. And René was talking about planets which are in the habitable zone around their star. So obviously there we are going to look at things like water, because it's very interesting to see what are the conditions there. Ultimately, that's going one step to an understanding if life is possible on other planets. And that's quite a quest, actually.
Yeah, I would just add that we'll have also the capability of detecting water clouds potentially in these temperate planets. So, and also that the mirror instant will have sensitivity to for the ozone molecule. So that's a very exciting molecule to look for. Ideally, quite difficult to detect.
As far as questions from the social media, we have sort of a follow-up on that. It says, will JWST observe the Alpha Centauri system, including Proxima Centauri and Proxima b, the exoplanet? Are there plans to observe that?
I'll take that one, Michelle.
I can take that one. There's plan that there are proposals to look at this planet, and a bit like Mars, this is a very bright target, and so we know that the Proxima b does not transit its star, and so one way to do it is by measuring either the reflected or the thermal component from the planet using the mirror instrument. So it will likely be observed with JWST. Yes.
Anything to add, Eric? Okay, sounds good. All right, we have another question from the media coming in. Operator, please.
Thank you. And once again, please press star followed by number 1. Should you have a question, that is star followed by 1. And we have a question from Bill Harwood. Your line's open.
Yeah, hi, this is number 3 for me. I apologize for that. And just FYI, guys, it took a really long time to get logged into this call, so I'm not sure how many reporters had the patience to stay on the line. But my question's for Lee again. Can you walk us through the light path and tell us a little bit about how an astigmat works, and with some emphasis on the steering mirror, exactly where that is in the path and how you use it to keep Webb so properly positioned? Thanks.
Yeah, so Webb is actually what's called a 3-mirror anastigmat, and that means that there's actually 3 mirrors that work together to form really the telescope. This is a little bit different than what a lot of people are used to. For example, in the Hubble Space Telescope, it's a Cassegrain telescope that's a 2-mirror system. So we went with the 3 mirrors to get this very wide field of view. And so you have the primary mirror with the 18 segments. You have the secondary mirror, which is out on that tripod that deploys. And then we have a large elliptical surfaced tertiary mirror that's inside of what we call the aft optic system. And that actually sends the light to what's called the fine steering mirror. The fine steering mirror is actually at a place where you actually get an image of the primary mirror. So it has a little mask around it that looks a little bit like the primary mirror. And it's a flat mirror, but behind it are special actuators that work at the very cold temperatures that all these mirrors work at, the minus 400 degrees Fahrenheit. And they point that fine steering mirror, and they work in tandem with the guider that Renee had talked about. The guider figures out where a star might be slightly drifting to as the telescope slightly drifts its alignment, feeds that to the fine steering mirror, and that fine steering mirror will keep us pointed, and it'll keep that image looking very crisp.
Thank you. And actually, this one as well, I think, is going to go to Lee. We have a question coming in about gold. So can you talk about why the telescopes are coated with gold?
Yeah, I know it does make it look good, but that wasn't the reason we selected gold. It turns out, if you look at the wavelengths of Webb, I mean, it's a very broad wavelength range, especially if you compare it, for example, to Hubble. It goes all the way up to 28 microns. That's the wavelength. But on the short side, it actually goes into the visible. So it's a very long wavelength range. And we wanted a material that would reflect the maximum number of photons. And so if you pick a material that doesn't do a good job of that, it's almost like having a smaller telescope from the point of view of sensitivity. So you really want to use the optimal material. And it turns out gold has an amazing reflectivity over all of these wavelengths. It's almost 98% reflective, so we lose very few photons. And the alternative materials just weren't as good in their reflectivity. So we really went for getting as much throughput as we could.
Absolutely. So going back to our social media questions, there's an instrument we should talk about a little bit more, and that's MIRI, our mid-infrared instrument. So the question is, what are some specific advantages of viewing the universe in mid-infrared as opposed to near-infrared? Would someone like to talk about MIRI a little bit?
Maybe I can say a few words about MIRI, and maybe Marcia will also complement. But usually astronomers, when we look at objects, when we look at different parts of the light, be it near-infrared, mid-infrared, we actually see the objects in a different way. We can see different components of the object. And Marcia was talking about the pillars of creation, where in the near-infrared, we just go straight through the dust and see what is hidden behind the dust. But this dust, when you go to the mid-infrared, it becomes suddenly it is an emitter of light. So you see the dust, so you can study its properties. So there are really very interesting things to use MIRI and to complement, as a complement also to the near-infrared observations. And when we talk about also a lot about these very first galaxies, and the very distant one, they get part of their light, which is shifted in the red, in the near-infrared, but also part of their light, which is shifted in the mid-infrared. So only MIRI on Webb will be able to see that. And this light in the mid-infrared contains additional information. As an example, on the existing population of stars, or slightly older population of stars in these galaxies. So this is really something that you can only see in the mid-infrared. So it's bringing a huge amount of new information and a very interesting new capability to Webb.
Thank you very much. All right, going back to our social media questions, we have one from Jonathan Amos of the BBC. The question is, what will you be able to see in the plumes of Enceladus and Europa? So once again, sort of looking for the signs of life. Would anybody like to talk about what we might be able to see in the plumes of Enceladus and Europa? I know that, Eric, would you like to talk about that?
Well, I'll just say that as a preface to that, Webb looks at things that are proposed by the scientific community. And so each year we conduct a competition and people put in their best ideas of what to look for. And so the question is about Enceladus and the water plumes and what might be in those plumes. And so certainly Webb will take a look at that to see what other chemical constituents there might be in those plumes with, again, a new set of eyes that we don't have, these infrared eyes, both near and mid-infrared. So if we haven't done it in that first year, we'll probably do it in the second year because the scientific community is always coming up with new ideas and they get to propose once every year.
All right, going more to social media questions. So Lee, once again, this is a question about the scheduling. This isn't a telescope that you just open up and it immediately works. You need to focus all of the segments. Can you give us a time frame as to when that will be happening?
Yeah, well, unfortunately, the reason we can't get things done faster is we're limited by physics. And really what that means is the cool down of the telescope and the cool down of the instruments. And you know, cooling to minus 400 degrees Fahrenheit takes a long time. And the instruments as well have to cool their detectors to a cold enough temperature that they're sensitive. So NIRCam will be sensitive a little after 30 days and the guider a little bit after that. And so we'll be using the guider and the NIRCam instrument to help us with the focusing, but we can't get started until they get cold enough. And then we can't actually align the telescope fully for another about a month because we need the telescope itself to get so cold that it starts to get really stable. And so it does take several months, but by about 4 months into the mission, during the commissioning, we should have the telescope fully aligned and we'll be handing it off to the science instrument calibration team for calibration.
Thank you. All right, I believe we have another question from the media. Operator, please.
Thank you. Our question is from Irene Klotz. Your line's open.
Thanks. I was wondering if the 4 instruments can operate simultaneously, or do they? Is that not possible? And also, is there some technical reason why the near-infrared imager was selected to be the wavefront sensing services over the mid-infrared instrument? Thanks.
Eric, would you like to start? Yes.
Sure, we'll start with the second one first. We've actually designed the telescope to be diffraction limited at 2 microns, which is in the NIRCam's wavelength range. And so that's why you want to use it to do the shaping of your mirror. And then the first part of the question was, again?
Could you repeat the first part of the question?
Yeah, if the 4 instruments can operate simultaneously.
Yes, in fact, they can operate simultaneously. We call this parallel observing, where you can operate more than 1 instrument at a time. And they may even be looking at slightly different pieces of the sky for different scientific reasons. But you can operate them at the same time and bring those data back and get even more science while you're doing one with 1 instrument.
Excellent. Anything to add? All right. Going on to our next question, again from Jonathan Amos on BBC. This one, I think, is going to go to Renee. How fast does the fine steering mirror have to move? How many adjustments a second?
Well, I guess that's a good one for Lee. All I can tell you is that we need to make these measurements 16 times per second. But I can't tell you exactly what the speed is this thing mirror. Maybe Lee can answer that one.
The loop closes at about 1 hertz. So that's about every second we close that loop, which is a little bit slow. You know, it's not super fast, but it's enough to correct drifts. And that's really what we're trying to do is the spacecraft slowly drifts, for example, thermally relative to the telescope. Those are the kinds of things. So there's slow effects we're trying to correct.
Absolutely. All right. So let's see. I'm seeing if we have any questions coming in on social media. Let's go to a question about using, okay, here's one. How much will Webb be able to determine the rotation rates of exoplanets, including potentially habitable ones, by tracking nature's surface features in optical or infrared? So is there a way that Webb has that will actually be able to determine rotation rates of exoplanets? Anybody want to talk about that one?
I can take that one. It's going to be very difficult to do that for a small rocky planet, but it's been done already with Hubble to detect rotation periods of gas giant planets, and by looking at and measuring winds in these atmospheres. So we think Webb will be even more capable of doing that. But for rocky planets, it's difficult. But we know from physics that in all likelihood these planets that revolves around their star, they're tidally locked. That is, they're always looking the same phase to their star. That is, they're rotating with the same period as their orbital period. Yeah.
Thank you very much. All right, we have a question coming in on social media about constructing the mirror, about where this material came from, the entire path of that.
Yeah, well, this is actually quite an amazing story, and it really was a team effort across the entire United States. It starts actually in Utah. That's where the beryllium was mined. We actually developed a new form of beryllium just for the James Webb Space Telescope. It's an optical grade that's more uniform than has been done before. And the billets of that, the blocks of that, were actually made just outside of Cleveland, Ohio. And then those blocks were sent to Cullman, Alabama. That's where they were machined. And there was a large machine shop that we built specially just for these mirrors. After they were machined, and that means lightweighting them and getting the surface rough, the mirrors were sent to Richmond, California. That's where they were polished. It's actually the same company that polished the corrective optics that fixed Hubble, which is, but this was beryllium and large mirrors. Then the mirrors were actually sent for coating just outside of Philadelphia. And they also made stops in Boulder, Colorado, where they were assembled. Ball Aerospace was the group that designed and assembled them. And ultimately, they made a trip to the Marshall Space Flight Center for testing. We actually had to test them at cold temperatures to determine how they deform and send them back for polishing and then back for measurements. And then finally, they made their way here to Greenbelt Goddard Space Flight Center, where the telescope was assembled.
Absolutely. All right, a question from social media again. How long are reaction wheels, gyroscopes, etc. on Webb designed to allow it to operate compared to how long the reaction wheels allowed Kepler to operate? Also, how many reaction wheels are there? More than 3? So it's about the reaction wheels and the gyroscopes and how long they plan to last.
Sure, I'll take that one. There are 6 on Webb, and they're different than the ones that were put on Kepler. I think the ones that are flying now that are analogous might be on the Chandra X-ray Observatory. So we anticipate them to have a very long life, and those aren't actually the life-limiting feature on Webb. Rather, it's our station-keeping fuel, which we have 10 years worth, at least 10 years worth of fuel.
Thank you very much. All right. So this is all the time that we have for today. Thank you so much to our guests, and thank you for joining us as we count down to the amazing launch of NASA's new James Webb Space Telescope. I'm Dr. Michelle Thaler at Goddard Space Flight Center. Thank you so much for joining us.
And thank you. This does conclude the call. You may disconnect.